Nuclear magnetic resonance, or NMR, is probably the most important technique for finding the structures of organic compounds. So much so that there is a saying, when the NMR goes down, the organic chemists go home. The principle of NMR is based on the fact that certain nuclei with odd atomic mass or atomic number, such as hydrogen-1, carbon-13, fluorine-19 and phosphorus-31, have a property called spin. This means that they have a magnetic field similar to that of a bar magnet. When placed in an external magnetic field, these nuclear magnets can line up in one of two ways, with or against the applied field. These two different states have slightly different energy levels. Electromagnetic radiation, which has an energy corresponding to the gap between these two states, can cause these nuclear magnets to flip from a low-energy state to a high-energy one. The size of the energy gap determines the frequency of radiation required. Each element has its own particular frequency, but they all lie within the radio part of the spectrum. We will concentrate on hydrogen-1 NMR. This is often called proton NMR because the hydrogen nucleus is just a single proton. As they drop back from higher to lower energy states, the nuclei of hydrogen atoms in different positions in the molecule give out energy at slightly different frequencies, and this can tell us a lot about the structure of the molecule. For example, in ethanol, CH3CH2OH, the three CH3 hydrogens will give a slightly different frequency than the two CH2 hydrogens, which will be different again from that of the single OH hydrogen. This energy is picked up by a receiver in the instrument and looks like this. A strong signal gradually dying away. This is the total signal from all of the hydrogen nuclei in the sample and is very difficult to interpret. However, a mathematical technique called a Fourier transformation can be used to separate out the signals from hydrogen atoms that are in different molecular environments and present them as a spectrum that can be interpreted by chemists. This is a typical NMR instrument. The magnet is a superconducting one and is housed inside the cylindrical metal casing. It is cooled to 4 Kelvin in a jacket of liquid helium, which in turn sits in a jacket of liquid nitrogen at 77 Kelvin. The magnet uses a current of 50 amperes, which, once started, flows continuously as the coils have zero resistance at 4 Kelvin. The sample sits in the centre of the cylinder inside this probe, which contains the coils that send and receive the radio frequency signals. The electronics which generate and interpret the radio signals are housed in the boxes to the left. Samples are placed in the machine and removed from it by the auto changer, which takes the samples in turn from the carousel. The instrument is controlled from this workstation. This spare probe shows the radio coils and where the sample sits. Here we will run the proton spectrum of ethanol. A small amount is taken and dissolved in deuterated trichloromethane. This solvent is trichloromethane, in which all the hydrogen atoms have been replaced by deuterium. This is so that the signals from hydrogen atoms in the solvent will not be mixed up with those in the sample. A little tetramethylsilane, TMS, is often added as a reference. Each molecule of this has 12 hydrogen atoms, all in exactly the same environment. The signal from these is taken to be the zero of the spectrum and has the value of 0 parts per million. Inside the instrument, the sample sits on a cushion of gaseous nitrogen. This plastic spinner has vanes that turn in the flow of nitrogen and spin the sample. The spinner is placed on the tube in such a position that the sample tube will be in the centre of the magnetic field when it is in the instrument. Together, these ensure that the sample experiences a uniform magnetic field. The operator places the sample in the auto-changer and tells the computer the identity of the sample and which position in the carousel it is in. The auto-changer selects the correct sample and places it in the instrument. The sample is lowered gently into the probe on a cushion of nitrogen so that it sits in the centre of the magnetic field and the radio coils. Under the control of the computer, the instrument applies several, typically 16, pulses of radio waves to the sample and collects the responses, called resonances. These resonances are summed up by the computer and processed to give a spectrum. This takes about 5 to 10 minutes. Here is the spectrum of ethanol. The peak to the far right is that from the TMS reference. By definition, this is at 0 parts per million, ppm. The distance leftwards along the horizontal axis is called the chemical shift, and it is measured relative to the peak that is obtained from the hydrogen atoms in TMS. The chemical shift of a peak gives information about the molecular environment of the hydrogen atoms that it represents. The peak at around 1 ppm is caused by the CH3 protons. That at approximately 1.6 is the OH proton, and that at approximately 3.5 ppm is from the CH2 protons. The area under each peak is proportional to the number of each type of proton. This is calculated by the computer and represented by the step height of this integration trace. A closer look at the spectrum shows that the peaks are in fact split into groups of peaks called multiplets with particular patterns. This is called spin-spin splitting. It is due to the influence of the magnetic field of adjacent protons. Two adjacent protons split a peak into 3 with heights in the ratio 1 to 2 to 1. And 3 adjacent protons produce 4 peaks with height ratios 1 to 3 to 3 to 1. This is sometimes called the n+1 rule. Interpreting proton NMR spectra can thus provide a great deal of information about molecular structures. The same instrument can be used for NMR of other magnetic nuclei. A useful one for organic chemists is carbon-13 NMR. All that has to be changed is the frequency of the radio signals.